Acceleration. Goals here are to talk about acceleration, to look at some equations we apply when the acceleration is constant. We'll look at free fall, which is a good example of motion for which an object has a constant acceleration. And we'll also learn how to interpret graphs relating to an object experiencing acceleration. So acceleration is a vector representing how fast and in what direction an object's velocity is changing. Acceleration is the time rate of change of velocity. The average acceleration can be expressed like this. A with a bar on top is delta v over delta t. And in the limit that time interval approaches 0, this equation gets us the instantaneous acceleration. If the acceleration happens to be constant, then the instantaneous acceleration is equal to the average acceleration. Okay, let's think about directions. So here we'll observe a motion when both the velocity and the acceleration are positive. Positive here we're defining as to the right. And again, in the second case, we'll look at in a minute, when both the velocity and acceleration are negative. Okay, so what you saw in that case is there was a velocity to the right, the dots were closer together at the beginning, farther apart at the end. The velocity was positive to the right, and the acceleration was also positive. Let's look at this next one. In this case, the velocity initially starts out to the left. Again, the dots are close together at the beginning, farther apart toward the end. In this case, the velocity is in the negative direction to the left, and the acceleration is also in that same negative direction. So complete this sentence. When the velocity and the acceleration are in the same direction, as shown in both cases here, the object speeds up, and that is shown by the dots on the motion diagram getting further apart. Okay, we'll do a similar thing. Now we have the initial velocity directed to the right in the positive direction, but the acceleration is in the negative direction to the left. So the velocity and acceleration are in opposite directions. So now we see the dots on the motion diagram get closer together as time goes by. Okay, in this case, velocity is positive, acceleration is negative. Okay, we'll do the other case. The velocity starts out to the left in the negative direction, but the acceleration is in the other direction, it's to the right. Once again, the dots start farther apart, and get closer together as time goes by. Okay, this is v is negative, left, and a is positive, to the right. So when the velocity and acceleration are in the opposite direction from one another, as shown in both cases here, the object slows down. Okay, here we have a great set of 4 equations we can use to relate displacement, velocity, acceleration, and time. We call them the constant acceleration equations, and they apply when the acceleration is constant. We also measure the motion from t equals 0. Note that everything in here except for t, the time, is a vector component, which means it's a scalar with a sign, and you have to put in the appropriate plus or minus sign to indicate the direction of that vector. One note about that last equation, that part, the position is the initial position plus the average velocity times time. That's true all the time. It's just this second part that's true only for constant acceleration. Okay, let's look at these in a little more detail. Where does that first one come from? Well, that comes from the definition of the acceleration. How about the last one? Well, that comes from the definition of average velocity. Once you have those two, then you can get the other two. Okay, so the second and third equations come from combining the first and the fourth. The second one you get by just plugging in the value of v, vi plus at, into the fourth equation. That gets you that third equation. The third one, that gets you the second equation, sorry. The third one comes from solving for t in the first equation and plugging that into the last one. Okay, we'll also make use of motion diagrams. Okay, so we've done this kind of thing before with velocity and speed. And note that velocity is connected to position the same way acceleration is connected to velocity. So we have the instantaneous acceleration of the slope at a particular instant on a velocity versus time graph, while the change in velocity is the area under the curve for a particular time interval on an acceleration versus time graph. Okay, so we'll do a free fall situation. We'll have an object being dropped from rest from a height of 20 meters above the ground. We'll approximate the acceleration due to gravity as 10 meters per second directed down. Here we'll show the corresponding acceleration versus time graph. Okay, so what you note here is that the acceleration is constant. It's a flat line at minus 10 meters per second per second. So we can use the acceleration graph to find the change in velocity as the ball falls. Note that the images on the motion diagram are drawn every 0.2 seconds. Okay, so we'll take the area under the curve. It's just a simple rectangle. And we'll find the area. The height of that rectangle is minus 10 meters per second squared, minus 10 meters per second, and the width is 2 seconds. So we multiply the height by the width and we get an area of minus 20 meters per second. What does that mean? That means that's the change in velocity. The velocity starts at 0 meter per second, so it ended up at minus 20 meters per second just before impact. That means 20 meters per second directed down. What does the velocity versus time graph look like? Okay, so here we see the same motion diagram. Now we'll plot velocity as a function of time. Okay, so here we see, in fact, the velocity versus time graph has a constant slope. It starts at 0 and it ends up at minus 20 meters per second. Velocity changes at a constant rate. That's consistent with constant acceleration. So let's check this, that the slope of the velocity graph is the acceleration. So let's find the slope. We can take the slope over the whole graph because it's constant. So we can say in that 2-second period, the velocity, the rise there was minus 20 meters per second in a time of 2 seconds. Slope is the rise over the run, minus 20 over 2, minus 10 meters per second squared. That is the acceleration, isn't it? So that is correct that the acceleration is the slope of the velocity graph. How about the position versus time graph? Okay, so we'll do that same motion diagram. We'll plot the position versus time graph. Okay, position starts at 20. The slope is flat basically at the beginning because the velocity is 0, and the velocity gets more and more negative, which means the slope of this graph, position versus time, gets more and more negative. Slope of the position graph steadily changes. And that is it for our introduction to acceleration.